All right. So welcome back, and so let's start this lecture with a quick recap of what we have done in the last class. So in the last class, we finally concluded our discussion on number systems. We looked at the two's complement subtraction in more detail. Okay, I hope everybody is clear with that. The way that we were doing things. Again, the idea here is two's complement not only helps in representing negative numbers or signed numbers to be more accurate, okay, but it also helps uh, in simplifying your hardware. Okay. Now, are you able to hear me? Okay. Very good. So, thank you. Now, so as we seen in the last class, the two's complement approach will also help you minimize the hardware, right? So now we can, because the approach is such that you're doing an addition, you're doing a subtraction operation as an addition operation, right? That's what it is. So in other words, if I were to design a hardware that would do addition operations, I would most likely be able to use the same piece of hardware to be also be able to do the subtraction operation, okay, using the two's complement approach. And of course, in this class, in one of those classes, we will actually see how that can be done, how we can actually design and add a circuit, okay, that can perform both additions and subtractions. All right. Now, toward the end of the last class, we also gave a brief introduction to the logic, the construction of the computer. Okay, again, in terms of looking at it as an hierarchical device, right? Hierarchical as in it has different levels of organization. Okay, and I can go to different levels of organization to see how these things come together to form the one unit. Okay, and we have seen that at the lowest level, okay, at least in terms of, I would not say it's the absolute lowest level, but with as it's related to this class, at the lowest level we have the logical gates. So these are the logical gates that come together that we can actually use to design simple modules, okay, and these modules are the ones that come together to form subsystems, and then putting together the subsystems forms more complex systems, and then these multiple complex systems form your entire computing device. So that's the idea behind the hierarchical architecture of a computing device. Okay. All right. So now, and so the goal in this class is to develop these rules. Okay, we want to come up with these rules by which we can actually use these logical building blocks, which are your Lego building blocks, if you will, okay, uh, and then putting them together in the right format to obtain what we want to obtain the functionality, the right functionality that we desire from these building blocks. Okay, so the idea is you start with very simple logical building blocks that can perform simple logical operations. Okay, and putting them together in the right format will give you more complex logical operation. So that's the idea behind this. And in the last class, we looked at as a first example, we looked at the AND gate. Just to recap, again, the symbolic representation was this. We have that's how the AND gate is represented as. Now, again, the AND gate, if you can go one more hierarchy there, and if you go one more hierarchy, what you will be looking at is the circuit level, where you'll be dealing with voltages and currents and these components, the actual electronic components. Okay, and we have actually looked into that. One potential way of realizing an AND gate is basically, you have two transistors. Okay, a transistor again is, as we discussed in the last class, for those of you who are not familiar with this is basically a switch. Okay, it's a switch that can be turned on or off based on what you apply on this terminal. You have an additional terminal called the gate terminal. Okay, so you have two transistors. Let me call this, so the input attached, let's say this is A, that's B, that's A, that's B, and that's your output F. That's your output F. Okay, and this is where you will apply your source voltage of 5 volts, let's say. Okay, now So this is the AND gate that can perform what is called an AND operation. Okay. So if I want to write this out, what it performs, I can write this as F is true, or let me actually write it as a statement. If I want to write this as a statement, F is true. Again, going back to our previous class, when I say true, I'm referring to the output being a 1. Okay. F is true if A, the input A, and so it's basically a logical operation. It performs a simple logical operation, right? If A and B are true, that is, if A and B are both ones, only then my F is true, my F is 1. Okay. For every other combination, for any other combination, my F is false, or false again, which means, so in terms of logic, I will say false to be associated with 0, true to be associated with 1. Okay. That's the convention. And we can also write or describe the exact same information that I wrote here in the form of what is called a truth table. Okay. And so we'll be using truth tables a lot in this class. So truth table is nothing but, in simple terms, you have A and B. Again, remember that A and B are digital inputs. They can only take 0 or 1 values, and we have already know that. So basically, we are all working with binary system. A and B can only take 0 and 1 values, 0 or 1 values, and then you have F. Now, so the truth table basically gives you a snapshot of exactly what it does, what this particular device does. Okay, so to complete the truth table, I need to look at all possible combinations between A and B. How many do I have? A can take 2 different possible combinations, 0 or 1. B can take 0 or 1. So that's 2 times 2 is 4. So basically, when I write down all combinations, I would contain 4 different combinations. And that's it. I don't have any other combination beyond that, right? And again, as according to this statement, F is true only when A and B are true. So everything else is 0 or false. So that's how the AND gate operates. And I can write this as an algebraic expression, okay, where I borrow the operators from your regular algebra. We call this Boolean algebra because my variables A and B are somewhat different from working with your conventional algebra. Right? My variables A and B can only take 0 or 1 values. So that's constrained to take only 0 or 1 values. So that the rules are slightly different, but most of the time, you'll see that they match. Okay. So in this case, I can write this as A and B. So AND operator, so my dot indicates an AND operator, okay, AND logical operator. Or I can also write this as AB. So I'm borrowing the product operation to represent the AND operation in this Boolean algebra. Okay. So that's the idea here. So F is AB. As soon as you see this, a product term, that means it's an AND operation. A product term indicates an AND operation. Again, it's a logical operation. The rules are very similar, but not exactly the same with conventional algebra. Indicates an AND operation. Okay. All right. Now coming back to this circuit, would this circuit actually correspond to this AND operator? All right. Now, again going back to the previous class, this is a transistor. Transistor is basically a switch. If I apply A equal to 1 or 5 volts here, the switch is closed. That means it basically forms a conductive path. Okay. If I apply A equal to 0 here, the switch is open. That means this part of the circuit is disconnected from this part of the circuit. Okay. So that's the idea. That's the simplest idea. You don't have to know beyond this, at least in this class, okay, to understand the operations. All right. So will it work? Let's say now with A equal to 0 and B equal to 0, both of these transistor circuits are open, right? with A equal to, when I apply these voltages on the transistor gates, both of these circuits are open, the transistors are open, the switch is open. Now what is the voltage across on F at this particular node? Now this particular resistor is grounded, right? Now my 5 volts is disconnected from this node, so obviously my F is basically 0. Okay. Now what about if A equals 1, which basically completes this circuit, but B equal to 0? Even though this completes the circuit, this is disconnected, so my F is still 0. What about when A equals 1 and B equals 1? Now in this case, of course, this is a complete circuit now. That means my 5 volts is connected, or my node voltage here is connected to 5 volts. In other words, my F becomes a 1. So this operates according to the AND operation, the way we have defined the AND operation. Okay. So that's how, if you go one hierarchy down, you can actually start seeing the circuits for the corresponding gates. Okay. So that's your AND gate. All right. Now we have other gates too. So let's actually look at those. Then you have what is called the OR. If you have a product operation, you should have a sum operation. So your OR is similar to the sum operation. And the symbolic representation for the OR gate is that. Again, remember that these gates can have multiple inputs. At this time, I'm just showing 2 for simplicity, but these can have multiple inputs. Okay. So you have A and B and F. Okay. Now, in terms of algebraic expression, I can express F as A or B. Now, the very important thing is that my algebraic expressions here, the Boolean algebra, is equivalent to the circuit. Okay, so just keep that in mind. So F is A or B. So as soon as I see this expression, this OR gate should come to my mind. Okay, so the circuits and the expressions are convey the same information, exactly the same information. Now, in terms of a statement, a logical statement, okay, I can write this as F is true. Again, this plus is an operator, it's an OR operator. It has properties very similar to the addition operation, but not identical. We'll see how. F is true if A is true, or B is true, of course, or both are true. Both A and B are true. F is true if A is true or B is true, or both are true. Okay. And in terms of the truth table, I can describe this as, again, that's my A, that's my B. I look at all possible combinations between A and B, which are 4. Okay. F is true if either of A or B are true, according to my logical statement. So here, of course, A and B are both zeros, so that's definitely a 0. And for every other combination here, one of them is true, so basically that's true. My F is true. So that's how the OR operation works. Okay. Now, as you can see here, when I say F is 1 or 1, this is not equal to 2. Right? This is because this is not an addition operation, this is an OR operator. So so you do have some subtle differences between the conventional addition operation versus the OR operation. So this is a logical operation. This is a logical operation different from arithmetic operation. Okay. Okay. And if I want to go down, so one hierarchy, okay, what would be a corresponding circuit or one potential way of implementing this or gate? Okay. So here is one. So again, you have 2 transistors. That's my F. let me call that A, let me call this B, and that's 5 volts. Okay. So my each of these transistors is individually connected to that 5-volt node point, just to supply voltage. Okay. Now, let's see if this actually corresponds to this operation. So you can see now we are able to utilize these circuits, right, to perform simple logical operation, which would basically be the starting point in designing more complex systems. Okay. All right. So if f is true, if f is, okay, both are of course zeros, right? If a and b are both zeros, then of course both of these are disconnected from the supply, and what I read at f is basically 0, corresponding to this condition, right? If one of them is true, what happens then? If let's say if a is true, b is 0. If a is true, this particular transistor is closed. That means this particular transistor closed, as in, this is closed. So this particular voltage now is connected to f, so f is true. Okay. Even though b is 0, this is open, but that doesn't really matter, right? So if one of them is closed, then the node voltage here would be 5 volts. So that basically correspond to this truth table here. Okay, so that's my OR operation. So f is true if a is true or b is true, or of course both can be true as well. All right, and then we have another gate called the NOT gate. So that's your OR. So let's be done with that. A NOT gate, again, it's a single input gate. Okay, and that's the symbolic representation for the NOT operation. So that's A, that's F. F is the output. Typically in these circuits, we'll represent the output as F. Okay, and symbolically, I can, algebraically, I can basically write F as not A. Okay, not A, or I can also write this as A prime. A bar or A prime doesn't matter. Let's say it conveys the same information. I would say this as a logical expression as not A. So simply, if if A is 0, if F is not A, the only other possibility is 1, right? Likewise, if A is 1, F will be 0, and so on. So that's the idea. Okay. So the truth table for this particular gate, NOT gate, would read as if A is 0, F is 1, A is 1, F is 0. Okay, so that's good. Now, what would be a potential realization of this? How do I realize this with a circuit? One potential way is, again, this is a simple potential way. So again, you have a transistor. All right, that's your gate. Let's say that's A, and that's your output F. That's 5 volts. Okay. Now, if A is 0, that means this particular transistor is open. There is no current flowing through this resistor, no potential drop across the resistor. My F will be 5 volts or 1. Right? So if A is 0, F is 1. On the other hand, if A is 1, that means I'm applying a gate voltage on my transistor. My transistor switch is closed. Okay, and now what do I have? Now a current flows through the resistor. You have a current flow path to the ground, right? And I have basically this particular node is now connected to ground, and the F will be 0, and it works. So basically, that can be a so you can actually fabricate or construct circuits that can perform simple logical operations. Okay. All right. Now together, these gates that we have just seen, the AND gate, the OR gate, and the NOT gate, these are also called, the combination of these gates is also called fundamental gates. Now, what do I mean by fundamental gates? Again, the idea is, if I have a large collection of these individual gates, I should be able to construct any computing device. Even the supercomputer can be constructed in principle if I have large enough number of these gates. So that's the idea. You can basically come up with any circuit, any computing device with just these three gates alone. Okay, you don't need any other additional logical operation or any other gate that can perform any additional logical operation. With just these gates, I will be able to construct any complex, whatever complexity it is. I should be able to do that with just these gates alone. Okay, and that's why they're called fundamental gates. All right, so now let's look at other additional gates that we have beyond these. Okay, let's look at what is called a NAND gate. As you can see, you have a NAND gate, some relation to AND gate, right? You have AND with an N here. So obviously there should be some relationship. A NAND gate is symbolically represented as, oops. Again, this can have multiple inputs, but at this time we'll work with two inputs, A, B, and F. Okay. Okay. And this is actually, now every time you see this dot, not the dot, but actually a bubble, this bubble, right? That represents a NOT operation. Remember that for a NOT gate, we had the symbolic representation, something like that. So basically this bubble represents this NOT operation. All right. So this is equivalent to saying you have an AND gate and a NOT gate that are in series, something like this. So you have A, B, and that's your F. So in other words, I can write my F as, for this NAND gate, okay, I can write my F as A and B. The output here would be A and B, but again you have a NOT operation there. That means I need to basically complement that. Or I can also write this as A and B whole prime. So that's your NAND gate, NAND operation. Okay. And in terms of the truth table, the logical operation would read something like this. So you have A, B. So that would be basically exact complement of your AND gate, right? Because NAND gate is nothing but the complement of the AND operation. So you have A, B, F. Again, all possible combinations. So the output will be exact complement of AND operation. And remember that for the AND gate to be true, my A and B, both of them has to be ones. Only then the AND gate was true. For every other combination of the inputs, my AND operation gave me a false, right? So for the NAND operation, for every other combination of the inputs, my output will be true. And for 1 and 1, for A and B, both ones, the output will be false. So if you compare this truth table with your AND truth table, the outputs are complementary, exact complement. So that's your NAND truth table. Okay. All right. So far, so good. Now, if I have a NAND version, like a NAND gate, which is very similar to the AND operation, but with a NOT gate, we should have, through complementary operation for the OR operation as well, right? So now let's look at that. And of course, as you may guess, that is called the NOR gate. And the symbolic representation will be very similar. So that's your NOR gate. And again, that's very similar to saying you take a NOR gate and you apply the NOT operation in the front. Okay, and that becomes your NOR gate. And if I want to write this again as an expression, that will be A or B. Right? The output here at this point would be A or B, and then you're basically applying a NOT operation over that. So that will be A or B whole prime, A or B prime, or I can also write this as A or B whole prime. Same thing. Okay. Remember that this is not equal to A or B. Just keep that in mind for now. Okay. A or B whole prime is not equal to A prime or B prime. They are not identical expressions. Okay. Now, what about the truth table for the NOR gate? Right. Again, that will be exact complement of your OR gate. Right. For the OR gate, if A or B had a 1, then the output was true. Right. So that means the output was true for all of these combinations. Starting with this, the output was true for an OR gate. All of these combinations gave an output of 1. Of course, for the NOR gate, that will be a complement of that. So in this case, my F is true only for when my A and B are both zeros. A and B are both zeros. For every other combination, that's going to be a 0. Exact complement of your OR gate. Okay? Because obviously that's exactly how your NOR gate works. Right? Okay. So these are your NAND and NOR, and together, well, I will not say together. So individually, NAND gates and NOR gates are called universal gates. Universal gates. Now, why are they called universal gates? What it means is if I have just one type of gate, but a large number of that gates, let's say if I have NAND gates, billions of those, okay. What it means is I can just use NAND gates alone, and in principle, I should be able to construct any computing device, even a supercomputer, with just NAND gates alone. Likewise, if I just have a large number of NOR gates available to me, then I should be able to construct a supercomputer with just NOR gates alone, in principle. And that's why these are called universal gates. Different from the fundamental gates, because if I want to use fundamental gates in construction, I should be having all of these gates, a collection of AND, OR, and NOT, to be able to construct my devices. For these, not necessary. One type of gate is good enough. That's why these are called universal gates. But how do I prove this? Right? So the way I would approach the proof that these gates, NAND and NOR, are universal gates is by first assuming that this condition is true. That means my AND, OR, and NOT are fundamental gates. Assuming that this condition is true, I will build up on that condition and prove that NAND gates and NOR gates are universal gates. Let me actually show that for just the NAND gate first, and then as an exercise, you can perform that for the NOR gate. Okay. Now, the way I would show that is if I'm able to obtain using NAND gates alone, all right, using just the NAND gates, if I'm able to obtain the AND operation, the OR operation, and the NOT operation, that means I have obtained each of these fundamental gates with just NAND gates, and because fundamental gates can be used if I have large number of them to be able, these can be used to construct any computing device. And since I've shown that NAND gates alone can be used to construct each of these gates, and in principle I've shown that NAND gates are universal gates. I hope that reasoning is compelling. Does it make sense? Any questions on that? Okay. So let's go about proving that. I want to show now using NAND gate, using the NAND gate or a collection of NAND gates, I want to show the equivalent implementation of AND operation, OR operation with just NAND gates, and the NOT operation. Okay. Let's start with the NOT gate first. How do I implement a NOT operation using just NAND gates? Let's say, so that's your NAND gate. I want to obtain the NOT operation by NAND gates. A NOT gate is basically, as you can see, it's just one input. It has one input, A, and the output is F. Right? How would I obtain the operation? Well, we can try this possibility. Right? If I combine these two inputs, making it one, call this A, call this F, would I actually obtain the NOT operation? How do I check this? I can check it by the truth table, and that's where the truth table actually comes into a lot of help here. Okay, the truth table for a NAND gate was something like this. Okay, 0 0 0 1 1 0 1 1. For the NAND gate, all of these outputs were true except this output, this condition. Right, that's the NAND truth table. Now, when I combine these two inputs to contain a single input like this, that means I'm looking at these possibilities, right? My A and B both has to be true, but both has to be the same because I combine them together, right? So these are definitely not possible now. So I'm looking at these two conditions. When A is 0, that means I'm applying both zeros, F is true. When A is 1, that means I'm applying both ones here, F is false. And that's exactly what my NOT gate actually does, right? It's not A. F is not A. F is not A. And we have shown that, yes, if you combine the two inputs together for a NAND gate, you will have a single input, single output, and it indeed functions as a NOT gate, as one of the fundamental gates. So hence, I've shown that this is basically that. It has the performance of this is equivalent to the performance of an actual NOT operation. So that's the easy part. What about an AND gate? Anybody suggest how we can obtain an AND operation using NAND gates alone? Yeah, Montgomery.
So what you do is you take two NAND gates, apply A to B to the first one,
Okay.
and then directly attach F of that gate to both A and B of the next gate.
Perfect. That's it. So basically what you're doing, you take two NAND gates, A to B, A and B to the first one, and you take another NAND gate and configure this as a NOT gate, just like this, right? And we call that F. Okay. And you will see that this is nothing but that equivalent to an AND operation. How does it work? Again, whenever you have a complement of a complement brings you back the same number, right? If I take the variable x, for example, or let's say, my A is 0, I complement that once, I get 1. Complement that again, I get back 0. Right? So in this case, a complement and a complement cancel these two complements, giving me back the AND operation. Okay. All right. So that's easy enough. What about OR gate? How do I obtain the OR operation now? Yeah, Montgomery.
You do the same thing that we did with the NAND gates, but use NOR gates.
No, we have this time I'm trying to show that the NAND is a universal gate. We still want to use NAND gates to obtain the OR operation.
You take three NAND gates then.
Three NAND gates, okay?
Take the first, so you apply A to both terminals of one NAND gate and do the same for B.
Okay.
And then attach the outputs of both of those into the inputs of the third.
Okay, very good. Perfect. So in other words, you're complementing A, you're complementing B here, and you're sending the complements of A and B to the third NAND gate to get F. Now, obviously, this is not as trivial as this one. This one, okay, you can explain it without a truth table. But this one, I think we should use the truth table to prove that this actually works. Indeed, and let's do that. So truth table can be very handy here. All right. Now again, going back to the fundamentals, the truth table for a NAND gate is if I have A and B applied 0, 1, 1, 0, 1, 1. That was 1, 1, 1, 0. That's the NAND gate. The truth table for a NOR gate, what we want to get is if I have A and B applied to the NOR gate, and that's your F, 0, 0, 0, 1, 1, 0, 1, 1. That's the truth table for a, I'm sorry, that's truth table for an OR gate, not the NAND. We want to implement an OR gate, OR operation, not an NOR operation. Okay, that's the truth table for an OR operation. Yeah, Monty.
Shouldn't the A be 0, 0, F 0 for the next truth table for OR gates?
Oh yeah,
Right.
you're right. I'm sorry, that's my mistake. That should have been 0, 1, 1, 1. Yeah, that's correct. So that's the OR operation. All right. Now what I'm trying to do here is, for this particular circuit, okay, I'm applying A prime and B prime to this AND gate, right? How do we do this? Let's me take another truth table, okay? Yeah, let me actually do this. Let me actually extend this truth table. So if this is A and B, what is A? So this will be A prime and B prime, okay? These are the outputs of these NAND gates. So if A is 0, A prime is 0. I'm sorry, A is 0, A prime is 1. B is 0, B prime is 1. A is 0, A prime is 1. B is 0, B prime is B is 1, B prime is 0. A is 1, A prime is 0. B is 0, B prime is 1. And that's 0 and 0. Okay. All I've done is just complemented A prime, A and B here. Okay. And then these are the inputs. This is A prime and B prime going to F, right? So this is my F. Okay. And this F is the output of a NAND gate. Okay. Now, if I apply 1, 1 on my NAND gate, what is the output I get? For a NAND gate, if I apply 1, 1, what is the output? 0. Good. And for the rest of them, for the NAND gate, going back to your truth table, for the rest of them, these should all be 1s, right? All right. Now you forget about this intermediate because we don't really care about this, right? What we really care about is, what are the inputs you're applying to the system? What are the outputs you're getting out of the system? That's all we are concerned with. We are really not concerned with what is happening inside. This is helpful, but we don't. At the end of the day, we don't need it. So just forget about this. Now you can compare this truth table to this truth table, and you'll see that they are identical. So indeed, you can implement each of the fundamental gates using just the NAND gates. Okay. So hence proven that these are universal gates, NAND gates and NOR gates. Similar to what we have done here, as an exercise, you should do this for the NOR gate. How do I prove that a NOR gate is a universal gate, right? I would encourage that you do that so that and utilize the truth table approach that we just followed here to actually come to the conclusion. Okay. Any questions here so far? All right. If nothing, then let's move on. Now we have two additional gates. So we have looked at the fundamental gates, the AND or NOT, the universal gates, the NAND and NOR, and we'll look at two additional higher functionality gates. These are called the XOR and XNOR operations. Again, these can perform logical operations based on two inputs, and this is how they will actually work. Yeah. All right. So let's look at XOR gate. These are higher functional gates because the logical operation that we get from these requires two or more fundamental gates. Okay. So let me explain this, and then you will actually appreciate that. So the XOR will be basically the symbolic representation would be something like this: A, B, and F. And algebraically, I will write this as A XOR B. So that's how you would write this as an expression. F is A XOR B. Okay. And logically, I can write F is true if A is true, or you'll see that it's very similar to the OR gate, but with just one condition. Or B is true, A is true or B is true, but not, but for, let me put it the right way. Okay. F is true if A is true or B is true, but not when A and B are true. A and B are true. So A and B are true. In other words, I cannot have F to be true when A and B are both true, because that will basically form your OR gate. Right? In this case, only one of them is true. So for the truth table, that would basically read as have AB and F 0 0 0 1 1 1 1 0. F is true when A or B are true, but not both. Oh, sorry, but not both. Right. So that's the truth table for a XOR gate. That's an XOR gate, XOR operation. Okay. Now I can express this operation in terms of the fundamental gates. Again, remember your fundamental gates are AND, OR, and NOT as something like this. So F is true if A, B prime is true, or A prime B is true. As you can see here, this is a higher functionality gate because you're using multiple AND gates to realize this logical operation, the XOR logical operation. Okay, and I would like you to focus on this to remember whenever you see this kind of an expression that corresponds to an XOR operation. You can simplify that, or in other words, you can write this in a shorter form in this way: A XOR B, A B prime or A prime B. Every time you see that as an expression, you can just simplify that or just write this in a shorter, more compact form as A XOR B. Okay, so that's your XOR operation. And the last type of gate that we will see is called the XNOR gate. Okay, XNOR. Again, as you may guess, because you have an N here, which corresponds to NOT operation, all you have is you have a NOT appended here. And my F would read, okay, let me actually take this out. my f would read as a x NOR b. So that's a circle with a dot. Okay, that's how I would represent for an x NOR operation, which is, or I can also, in terms of XOR gate, right? Because you have an XOR gate here, and you are applying a NOT operation at the end, at the output end. So I can also write this as, XOR gate that is complemented. Okay. All right. And in terms of the truth table, that will be the exact complement of your XOR gate. So you have A, B, and F, 0, 0, 0, 1, 1, 0, 1, 1. For the XNOR gate, you have A and B has to be the same value. It can be 0 or 1, but not different. As long as A and B carry the same value, then F is true. So that's how the XNOR logic works. Okay. And again, this is a higher order gate. I can write this as a combination of fundamental gates as A prime, B prime, or A bar, B bar, or AB. So every time you see this expression, you should recognize that this expression corresponds to a next NOR operation, and you can write that expression in a more compact form using this notation. Okay. All right. So now we've covered all the kinds of gates that we should know. The fundamental gates, which consist of AND or NOT. The universal gates, which are comprising of NAND and NOR, and the higher order gates, which are basically your XOR and XNOR gates. Okay. Now, as I mentioned before, the goal for us as engineers is to come up with ways to put them together. These very logical building, the simple logical blocks that can perform simple operations in the right format to give us more complex logical operations. Okay. All right. Let's take an example now. Because this is all logic, instead of writing in terms of A's and B's, right? Now we can actually give some value or meaning to these inputs. Now let's again go back to the previous class when we talked about the logic, right? Let's say I give a meaning of A to be true, or A is 1, if it's a Tuesday. Okay. And let's say B is true if it's a Thursday. And C is true if it's 12:30 a.m. or 12:30 p.m. And I would define my output F as true if it's time for yearly 250 class. So now you made this logical decision to come to this class based on these input parameters, right? So in your circuit, so basically if I want to construct a circuit that can tell me this based on these parameters, I want to construct a circuit F using this building. Let's say for now, let's just focus on using ANDs and using the fundamental gates for our construction. Okay, so I want to construct a circuit, a simple logical circuit, okay, that can tell me when it's time to go to the class. How would I do this? I would probably start with a statement, right? F is true because if I write a logical statement, they can give me some idea about how do I put together these components, these circuits, to realize that this logical operation. Now, if it's true, or it's time to go to the yearly class, if A is true, okay, can write it in multiple ways. Okay, A is true. Let me say, A is true, and B is true. I'm no sorry. Let me put it this way: if A is true and C is true, right? That means if it's Tuesday and it's 12:30 p.m. or the other possibility, every time you see this and or, again you can associate that, yes, with the operations, logical operations, right? Or B is true and C is true, right? Now it's a matter of converting that statement into an expression. What would that be? So F is true if A is true and B is true. That means it's an AND operation and B is true. Or, I'm sorry, not B, C. Or B is true and C is true. Okay. So it's AC. Wait a minute. Yeah. So F is true if AC or BC are true. Right. Now you can already see it's performing slightly higher level logic operation from individual gates. Right. Okay. So of course this is a very simple example. Right. And what would the circuit look like then for this one? Again, remember that every expression that we come up with is equivalent to a circuit, and you should be able to, immediately visualize in your head what would that look like. So F is AC or BC. Now this is an AND operation, that's an AND operation, and between those two AND operations I have an OR operation. Right? So I have two AND gates represented by these two product terms. Every time you have a product term, that represents an AND operation. Some terms represent the OR operations. Okay, two ANDs. So I have two ANDs, A, C, B, C, and the output of these two are going into an OR gate. Right? And that's your F. So the statement and the circuit are equivalent. Very good. Now, in real life, of course, we are dealing with much more complex logic. We want to build complex logical circuits. This is much more simple. Okay. How do I do this? So typically what is done? Yeah, Samuel.
Could we do this with one AND gate and an OR gate?
Okay.
So have A,
Go
A
ahead.
or B,
A or
and
B.
then the output of that goes to one AND gate.
Can you repeat that? F is A or B?
So we have an OR gate,
Okay, we have an OR gate.
and then the output with A and B attached as inputs.
Okay.
And then could we connect the output of that to an AND gate, or the input to an AND gate, and then the other input to C?
Okay. Something like that.
Yes.
Well, let's see if that makes logical sense. That's a very good idea. I'm glad that you're looking at alternatives, and that brings us to another important question, right? Now, when I'm trying to build this logic, how many different ways can I achieve the exact same logical operation, right? Okay, let's see if that works. So that basically, so here, F is true if I want to write this, yeah, what would be the algebraic expression for that? F is true. I have one OR operation here, so that's A or B. So that means, again, I defined A and B to represent Tuesday and Thursday, right? F is true if A or B is true, okay, which is good, and C is true. Perfect. This should work. Absolutely. So F is true. So as you can already see, the original circuit that we came up with contained one additional gate. Here, I have just two gates. Well, that's a good point. Okay, so let me read that chat out. Let me actually see what you have. That logic be false as that it implies it can be both Thursday and Tuesday. Yes, it can imply, but it could be both Thursday and Tuesday, but that really doesn't happen in real life, right? In real life, you cannot have it both Thursday and Tuesday, though that condition is automatically cancelled out, and you don't have to worry about that. It's not going to happen. If it happens, that's fine. If it doesn't, and it's not going to happen, which is fine too, it still works, right? You could use an XOR gate, but I would not need an XOR gate. That condition doesn't happen. I don't care about that condition. In fact, that's again you're thinking ahead, because we're going to look at those conditions when we're designing systems. We do come up with conditions that may never happen, and that will actually help us in designing simpler circuits. Okay, but hold on to that thought. I'm glad that you're actually thinking through here. At least for now, does it make sense? Does that satisfy you? Your question, comment? Are you good with that? I agree with you that yes, A and B here, the way I wrote this implies that A and B could be both true, right? Which does not make sense physically, but which is fine. So that condition doesn't happen, and F is that doesn't really change the outcome of F. Okay. All right. So yes, that's absolutely right. So the take-home message is, when we're trying to build a logical circuit that can perform some function, it does not need to be the most unique solution. You can have multiple solutions that can do exactly the same logical operation, and that's readily demonstrated right here with this expression. Okay, great. All right. In real life, of course, we are dealing with we want to design more complex logic, so we need to derive some rules by which we are able to do that. Okay. Now, oftentimes, let's actually take another circuit, another simple expression. Let me say F is A or B C prime. Okay. Oftentimes, what we are given as engineers is you're given a problem statement. Let's say you're trying to design, or somebody comes to you, your client, and asks you to design some kind of a control system, okay, like a traffic light controller for a particular intersection. Okay, and then you need to formulate the rules, and you need to understand the conditions. Okay, what your controller should be doing in the first place, what are the inputs to that controller, and how many outputs, and how these outputs should respond to these inputs. And that's how you would basically come up with, and then you use the rules that you have learned in the design to put together and design your control system for that particular application. Okay. Now let's say you have an expression, something like that. It's a logical expression. Okay. You have three inputs here. Okay. A, B, and C. You have three inputs. Now, again, just like what we have done in the previous example, let's see if we can actually give some meaning to this. Okay. Let me suggest that my A, in this case, this corresponds to a like a nuclear reactor setting, and we want some decision logic by which we can know when to shut down the reactor. Okay, And again, as in a reactor, like especially in a nuclear reactor, you can imagine that you'll have multiple sensors, right, that are monitoring different conditions of the reactor. So let's say, your A represents, again, remember that, okay, let's actually go back to this expression now. If F is A plus B C prime, the logical statement corresponding to that would be F is true if A is true, right? So A takes the precedence, is true. Or, so as long as A is true, then you don't have to worry about what happens to B and C. So F is true if A is true, or B, because now B and C are kind of coupled together. So B and not C are true. Not C is true. So this product of B and not C has to be true, or F has to be true for my A has to be true for my F to be true. Okay. So as you can already see, my A kind of takes the precedence here. So let's say if I want to come up with some kind of a meaning, as an example, you can just as one potential example. Let's say this represents a decision logic to shutting down a nuclear reactor, and the input A corresponds to the sensor input that indicates that if it's true, implies you have some kind of an overheating happening in the reactor, and it has to immediately shut down. So as soon as your sensor becomes true, the value of the sensor becomes true, then it's time to shut down the reactor. Don't worry about what happens to B and C, because that comes next. Now let's give some meaning to B and C now. What about other times when it's not overheating? I shut down the reactor when B, which indicates if B is true, that implies it's a weekend, let's say. So the nuclear reactors are shut down on the weekend. Okay. But you also have C coupled to B. So let's say C represents, C is true if, let's say, maintenance is scheduled. Does it make sense? Let's see if that makes logical sense. Because if you have maintenance schedule or no maintenance schedule, let me put it this way. C is true if there is no maintenance schedule. Is that so? If no maintenance schedule, it should be maintenance schedule. Okay. So I'm giving some meaning to another logical expression here. A plus BC prime. F is true if it's overheating, then it has to shut down. Or it's a weekend. B is true. Okay, if it's a weekend, B is true, and not C. Right? That means there should not be any maintenance schedule. So if C is true, that means maintenance is scheduled. C is false, that means maintenance is not scheduled, right? So it's a weekend and there is no maintenance scheduled. Then also my F is true. Some meaning. I guess just wanted to, every logical expression, it's not just an expression. Your variables have some meaning. Okay? This is just an example of, giving some meaning to a simple logical expression like that. Okay, does that make sense? Now, let's say that you're not given this expression in the first place. Okay, we started out with this expression, right? Let's say you're not given this, and a client comes to you, and he wants to design a control system or a decision system that would correspond to this operation. So if the client says, okay, I have these inputs, you have to construct a circuit that would be something like this. Okay, so that means my F is true if it's not overheating, or it's a weekend and there is no maintenance schedule. So that's what the client gives. That's the information your client gives to you, and it's your job to construct this circuit using the rules. Of course, this is actually a very simple example. You can directly write down the expression without really thinking much. But what if it was much more complicated one? Obviously in a nuclear reactor, you have multiple sensors, not just one or two. You have multiple of these coming together, and you have to make a logical decision based on all of those combination of these sensors. So it's going to be a much more complicated effort. Okay, I wanted to just trivialize it just for the initial example. So what you're trying to design here is this one, is a circuit, a block. So I would always go with the start with what is called the level 0 diagram. So that's your level 0, a broad overview of your project, right? So you're given this problem, you're looking at the level 0 diagram of this, 35,000 feet of your project, just showing you what are the inputs going to your system, what are the outputs coming out of your system. Again, when you're trying to design these circuits, you can have multiple outputs coming out of these blocks. In this example, of course, I have a single block. Okay. Now, so I have this information. That's the block diagram. Okay. Next, what I do, I would, and this is again the approach that we will take, given a problem statement, how would I design these circuits? Okay. How do I come up with a combination of these building blocks, the Lego building blocks, in the right format that would conform to the product specifications, or that would conform to the problem specification. Okay. All right. So next step in this design process, so I got this, that's the first step. I put that information down in terms of the block diagram. I'll call this the level 0 diagram. And then I would examine the relationships between A, B, and C and F, the inputs and the outputs, through the truth table, using truth table concept. Okay. So let's do that. So that's done. Okay, let's see. All right. So now we are going backwards. Again, we don't know what the circuit would look like. We are assuming that, so we are just starting with the description, the problem specification, and trying to look at the approach to get to that circuit level implementation. Okay. Now for the truth table, again, that's going to be a table between the inputs A, B, and C, and the output F. Okay. And your AB. Okay, so how many possible variations would I have? How many different combinations of inputs do I have here between A, B, and C? If I write down all possible input combinations, how many combinations would I have? Again, remember, A can take two values only, 0 or 1. B can take two values. C can take two values. So the total combinations will be 2 times 2 times 2, which is 8. Okay. So if I have, let's say, n inputs for my block, then the number of combinations in my truth table for the inputs would be 2 power n. Okay. For n inputs, that will be 2 power n. So for 3 inputs, that's 2 cubed. So that's 8. Right. So let's start with 0, 0, 0. Again, I will always follow this order, the numerical order. Okay, so 0, 0, 0 is basically the binary value is 0, right? 0, 0, 1, the binary value of 1. 0, 1, 0, the binary value is 2. 0, 1, 1, 3, 1, 0, 0 is 4. 1, 0, 1 is 5. 1, 1, 0 is 6. 1, 1, 1 is 7. So I have basically 8 combinations, 0 through 7, 8 combinations. All right. Now let's look at F. Again, my F is true if A is true. Regardless of B and C, if F is true, if A overheats, right? The sensor overheats or the system overheats, then the sensor A kicks in. If A is true, that means that's indicative of that fact that the system is overheating, though that's true. So I can already directly write here For all these combinations, my f is true. For what other combinations my f is true? Again, for now it depends on B and C, right? F is true if A was true, which is accounted for here, and or B and not C is true. So B has to be true, and not C has to be, and C has to be 0, right? So now that makes the product B times not C will be 1 times C prime will be 1. 1 times 1 is 1. So that will also, that possibility also gives me a 1 as my output. And then that will be B is true, but C is also 1. That means a maintenance has been scheduled. So the factory is not shut down. The reactor is not shut down. That's 0. That's also 0. And that's 0. So the truth table corresponding to the problem specification for the example that we just took corresponds to this. Okay. Now, moving forward, what we want to do is from this truth table, I want to get an expression of a logical expression based on this truth table. Okay. How do I do this? Now, f is true for this condition. If my input combination is this, or my input combinations are these. Right? F is true if my input combination is this or these. If those input combinations occur, f is true. Okay. All right. Now, to be able to translate that information in the form of an actual expression, because every time I see an expression, that's basically a circuit, right? Expressions are equivalent to circuits. Logical expressions are equivalent to circuits. So what I will do is I will define a new concept called minterm. We may not be able to finish this today, but we'll have this in the continuation in the next class. A minterm, concept of minterm. What that means is, okay, so let me define the attributes of a minterm, and maybe we can actually, together we'll form the minterms. A minterm is number one, it's a product term. It has three attributes. It's a product term between all the inputs, which in this case I have three inputs. In this case, again, that will be a product term between A, B, and C. Next one. The other attribute is each input combination. Okay, each input combination will have its own minterm. Each input combination will have a unique minterm. A unique minterm. That's important. It's unique. Third attribute is that each minterm, or the product term in this case, should produce a unique signature for that input combination. Unique signature for that particular input combination. So these are the three attributes of your minterm. Okay, it should be a product term. Each input combination will have its own unique minterm associated with it, and each minterm should produce a unique signature. What I mean by this is that if I input any other input combination to that minterm, that unique signature should not be happening. That unique signature should happen only for that minterm associated with that product term. Okay. All right. Let's take an example. It should be a product term between all the inputs. So let's say, let me call this minterm here ABC. Will that work? Let's take the example of ABC, because again, That is the product term between all the inputs, A, B, and C. That's the product term. Okay, so the first criteria is satisfied. Okay, now let's go to the third criteria now. Now, does it produce a unique signature for this input combination? When I plug in 0, 0, and 0 for these ABC values here, what is the output of this minterm? That's A and B and C, right? For an AND gate, if I have all zeros, or in fact, if I have even one input is a 0, the output of the AND gate is 0. Right? It's an AND operation, very similar to your product operation. X times 0 is 0. Right? So in this case, that gives me 0. What about if I plug in these values into this minterm? What do I get? A 0. Right? Okay, that's a good question, Julia. Now, for now, when I'm writing these minterms are basically specific to the inputs. It doesn't really care about the outputs. Okay, I can have another output from the same inputs. Okay, but these minterms are associated with the input combinations only. It doesn't care about the output. So for now, forget about the output. Even just forget that the output exists for now. Okay, so that's the idea. So obviously, this does not satisfy this criteria, because if I plug in this input combination into this minterm, that also gives me 0. So all of these combinations except this combination gives me 0 for this combination. So obviously, A, B, and C, the product term A, B, C, is not a minterm for this input combination. But we have a hint here. I know, but this product term could be a minterm for this combination, A, B, C, right? Because if I plug in this value, 1, 1, 1 into this product term, that gives me a 1. And for any other combination of these inputs, if I plug in these values to ABC, that's going to give me 0. So that's unique. Yeah. So this product term is a minterm corresponding to this input combination, not for this. So likewise, we should write or come up with product terms for every input combination, and then we'll take that up from the next class. Okay, so let's try to come up with these minterms and max terms. In the next class, we'll actually come up with the expression. Okay, so with that, we're out of time. So let's actually wrap up our discussion here. Any questions before we move on?
So, do you have the exam next week?
Yeah, I'm going to send out the announcement. The next, we'll not have the exam next week, but it's going to be the week after. Okay.
Okay.